So, in the last lecture, we understood that there are different types of OSs, and although there are different kind of OSs, there are some common components, okay, uh, which can be shared by these types of OS. Now, we, we can use these common components and we can and arrive at some common services given by these different types of OSs, right? So, what are these services? First one is user interface. So we looked at user interface, like there can be built-in command interpreters or there can be external command interpreters. We looked at shell, wherein you'll type a command and the shell will load the program into the memory and the program will execute. So there are also graphical user interfaces where you can use a mouse and you can interact with the computer and you can double click on certain entity and it will open it for you. So this is a user interface, and the user interface is how you interact with the computer. It can be command line, or it can be graphical user interface. So the second point is program execution. So the OS is responsible for loading the program into memory. Okay, so we have a program and we are going to give it some CPU time so it can does some work. We something has to manage its execution, right? It allocates CPU time and resources as needed. Like this is this is CPU. Process one is executing. We've given it the CPU and it needs some resources. Let's say uh, input output requests. Okay. Then once this is done, again it will be given some CPU time, or more memory or more peripherals. So for example, let's say you double click a browser, the OS loads it from disk to RAM and gives it some CPU time and starts execution. And what happens if it crashes? Not only input and output, let's say terminates or some error happens, it's crash. Then also it should give some appropriate response to the user back. So the OS has to manage all of this. Program execution, none other terms managing the uh, process and its execution. Mm, Execution by allocating CPU time and resources as needed. Right. And we have input output operations. This is not needed. So, say this is a keyboard, and every time you type something, it will be displayed in the monitor, right? And the intersection is over. So this is very simple. So every time, every input, keyboard or mouse, all this is handled by OS, and it provides a standard way, a standard um, way for programs to do input and output without directly controlling devices. So, what it means is if you want to print something and if you want to type something out on a monitor, you don't have to go and tinker with the hardware directly. You just have to enter or click something on the keyboard and it does, and OS does the rest for you, other things for you. So, this is what input and output operations mean. And we have file systems. And we looked in the last example. There's a user mode and there's a kernel mode. And kernel mode will go to disk. There are files sitting in the disk. It takes a file, let's say file one, and it can perform some operations like read or write, let's say delete or open, something like that. And uh, if all these operations are done, let's say we've read something and it'll give a response to the user mode again. So this we need to have a proper established way or streamlined communication with the disk to do all these file manipulations. So the OS allows programs and users to create, read, write, all those operations. I'm putting it as CRUD, create, read, update, and delete. Okay, and ensures the operations. mm, These operations follow rules. What kind of rules are these? Like whenever a file is going to get opened, this is a file, it is going to, something is trying to access it, it has to, the file has to be shared, okay, with this process. And when this is happening, another file shouldn't try to update or write uh, on this file, because process one is already doing something with the file. Let's say it's updating something, and process two is also updating something. Probably there will be some clash. Or let's say process two has already updated, but it did not close. Okay, the file is still open. Process one reads something. While the process one is reading, process two is updating again. So process one is missing some of the updates given by process two. So it has to be in a synchronized way. So these are the things. Other thing is communication. Let's assume you're on a Zoom call. This is the monitor. You're on a Zoom call, and this is you. So not only the OS has to operate the camera, it also makes sure of audio signals. And it's not just that, it also network. All of this, all of this camera and audio signals has to go to this network, and it has to go to the person too. So everything is going to be streamlined through the network. So the OS should all these process, this is another process, this is another process, all this process to communicate, and here another communication. So within the same system or between different machines over a network, that doesn't matter. But there has to be some communications, an established way or protocol to communicate properly. So these are some common services that are offered by the operating system. Now, what we'll do is we've talked about many things up until now, and we'll try to put it as one simple structure. So basically, this is a traditional Unix system. We'll put everything in one structure, and we'll sort of try to understand on which layer what is sitting in which layer. So on the top layer, of course, we know there are the US. On the bottom layer, we have the hardware like terminals, keyboards, or disk, magnetic disk, or hard disk, or RAM, whatever. And we have physical memory. Uh, so all these are present in the bottom layer. So in the second layer, we have shells, commands. So this is an interface basically. This is an interface. If the user or the application want to communicate with the underlying structure, it has to go through this layer. And there are compilers and interpreters. Oh, I'm sure if there's a program, is a line by line execution, and there has to be a compiler or an interpreter to check whether this program is correct or not. So basically, these are like compilers and interpreters are like professors, right? They'll check the scripts written by the students and whether it's right or wrong. Uh, we'll say. So, and we have system libraries. Sometimes these professors they don't know everything, right? So we have to refer some books. So like that, these compiler like these programs will make use of some system libraries like established frameworks, like to do some work. Uh, so all these system libraries are predefined tasks. This process maybe does a system call or maybe an API call to the system library, gets a framework and works on that thing. So we have these here, and this is exactly why we need message passing and communications. One of the operating services, operating system services. And the third layer is the kernel. I mean, system call is an interface to the kernel. This is the kernel, which is the brain of the OS, right? So what does this kernel do? This kernel handles signals and input output using terminal. Let's say you're pressing Control plus C. You want to copy something. You're giving a signal. You're going to trigger a signal, and the kernel immediately it will understand. Oh, okay, this user wants to copy something. Maybe that is why he's pressing entering Control plus C or the backspace. So this is done by the kernel. Also, the OS user blocks input output for file access, and we just looked at why synchronization is important when handling with files, and swapping via disk and tape drivers. So again, it talks about the synchronization part. What happens when a file is opened, and how we are going to swap contents from one thing to another. That is there. And the OS schedules CPU and manages memory. Like what is scheduling CPU? So let's say there's a pool of programs, okay? All these are programs, and everything is waiting to use the CPU. But now the question among this pool of programs, which is going to get going to go to the CPU? So the kernel is going to decide that it has some algorithms on its own, like first come, first serve, or there is Robin Hood, there's shortest time first algorithm. There are different algorithms, which of course we'll be looking for the lectures, and the kernel will try to handle it. So these operations are going on in kernel level, and if the kernel needs some hardware, then it uses the interface. Again, some interface is going to happen. So that layer is this interface layer. So here we have the all the terminals, peripherals like keyboards or printers or pen drives, something flash drives. Disks and tape, your hard disk, and physical memory, probably the RAM they're talking about. So this is a traditional Unix system. Now, is this the only system? Of course not. We have microkernels, okay? So in the last lecture, I mentioned the design of OS should be as minimal as possible, and it has to be effective as well. So the design should be minimal, and the effect. it should be maximum. So in microkernel architecture, the operating system keeps only the most essential functions. See, the most essential functions inside the kernel, like interprocess communication, CPU scheduling. We know what CPU scheduling is, and we have memory management. In memory management, we'll talk about paging, swapping, segmentation, virtual memory. All those we'll talk in memory replacement. See, memory management. And all other services like device drivers, we know what a device driver is. It's an interface between the software and the hardware. Uh, and, and file systems or application programs are moved to user space and run as separate programs. So this is the user space, this is the kernel space, and the messages will be communicated like this. So this is message passing. Okay, this is message passing. So this design improves modularity and stability. Modularity, in the sense, it will neatly arranges things in a segmented manner. And stability, how stability is promised here? Because if you're going to do some changes to file system, this is not going to affect the rest of these things. If you're going to do some changes to device drivers, the rest of the components will be safe. So this brings in stability. Microkernels rely heavily on message passing. Okay, so there's a lot of communication that is going on between user level services and the kernel, which can lead to slightly higher overhead compared to monolithic kernels. So the but increases security and fault isolation, right? Uh, uh, so there was a big debate between the founder of Linux, Linus Torvalds, and there's another uh, uh, big shot in operating system field. I don't remember his name right now. So this big shot mentioned or was a strong advocate of microkernels. He said the future is microkernels, but evidently we can understand that's not the case, and Linux is everywhere. Linus Torvalds is he is a strong advocate of monolithic kernels. So he says that having a monolithic kernel is very it's simple because there won't be much overhead in communications. In microkernel, there has to be a lot of message passing, so we have to keep track of a lot of information, and and it is prone for errors. So this is microkernels to you. And now the idea is all these OS structures basically does some work. Okay, this essence. This is important work for the user. Okay, or programs, whatever. But is there a way to measure how much work has been done? Is there a way to measure it? Yes, of course, the answer is yes. And how we are going to do it with the help of process. Okay, process. The basic definition of process is a program in execution. Also, it's a unit of work. Unit of work. Right. Now, why process? Why not time? So time is a good quantifier, isn't it? Like I'm going to teach for 6 or let's go. I'm going to see teach for 20 hours a week. Okay, I'm going 20 hours a week, and let's say I'm going to get paid for working 20 hours. This is a good model. Let's say, and after at the end of 20 hours, let's say somebody is going to come approach me and going to say, "What have you done in 20 hours? Do I have a solid proof?" And if I give him a piece of paper which contains nothing, or if it contains a bunch of rubbish, probably I won't be getting paid, isn't it? I have to do justice for the 20 hours I've worked. So much like that. So if a computer, let's say a computer is working for a timeline of 20 hours, and in the middle, 15 hours, it does nothing. It's going to sit idle, waiting for input output request. Okay, something is happening. It's waiting for input output. 15 hours is sitting idle. Only 1 hour and 4 hours. Only working for 5 hours. This is not a good model, right? So that is why we have a process. Uh, now what's a process? What's a process? So imagine process as a container. Uh, so this is a process. It's a container, okay, and it has some components. This is called a stack, and this is called a heap. This is where the data is. This is where the text is. Okay. So these are some components. And what does these components do? So this is where the process, like where the process is currently in execution. Okay. So it tracks all the function calls, all the local variables, return addresses, everything will be maintained here. And what does a heap do? It tracks how much dynamic data the process creates. To give us very simple example, let's say A is equal to 2, B is equal to 2, C is equal to 2 plus 2. Okay. This is a program I'm giving this and the CPU is going to calculate this and I'm going to get an output C A is equal to 2, B is equal to 2, C is equal to some operation is going on. So I'm going to get 4. And this is a new data. Okay. This is going to be returned. So my stack is going to return this. My stack is going to return this, and this will be saved in heap. This is a new data that is produced. So this is being produced dynamically. So it is saved in heap. So this is how stack and heap works. Mhm. And what is this data? Hmm. All the global and static. So these are things that don't change. So uh, local variables are within the scope of a function. Let's say this is a function, and all the local variables will be saved here. And this is visible only to this function. If there's a function outside, so instead of function, let's keep it as an object. Okay, and this is another object, object A and object B. This object B cannot access this local variables, but if there is a global variable, object A can object B can use it, and object A as well can use it. So the visibility differs. So all this global data and static data are saved in this section called data. Static variables. There's another name called persistent persistent state. Now we have text. Text is basically code. It says what work to be done. And of course, this process has some memory, some space is going to be allocated for the process, 0 to maximum, whatever it is. So now, based on these components, we can have some information about the work that has been done. So the code says add something, the code says add something. This the line by line instructions will be executed with the help of a stack, and the results are saved in the heap. And if there is a global data which is of need, that will be in this layer. So we have things going on, and the heap grows in this way. The heap grows in this way, and the stack grows in this way. So we have something going on. This process is going to be a runtime entity, and this will grow or shrink in its lifetime. So things are rolling right now. Now we have some information about the process. Lots of computations are going on. Based on the information, we can assess what the process has done.